All right, crew, so we're on chapter 2 homework, and before I get into it, I kind of want to talk about a few things. So the first is equations. So in class we said that C equals lambda nu, and we said if lambda goes up, C must go down, or nu must go down, and vice versa. If you remember, this one is, scroll that out, this one is wavelength, and this is frequency. And we said that this is speed of light. Okay, now in some other videos, and depending on your semester in class, we will talk about the one kind of master equation that we look at, because we also at some point said that E equals HC, or excuse me, H nu. And because C equals lambda over nu, we can go over here. Nu. And we could solve for nu here by dividing both sides by lambda. And we found out that nu equals C over lambda. In other words, E not only, I'm going to rewrite it so it's a little clearer, E not only equals H nu, it also equals HC over lambda, because we just took the nu and we replaced it with H over C. And as we talked more, you find out that it's also equal to a very specific number, which is negative 2.18 times 10 to the negative 18 joules. It's the amount of energy it takes for an electron to shoot out of an atom, a single hydrogen atom. And we multiplied that times 1 over n final squared minus 1 over n initial squared, where n were these energy levels we talked about. So if you remember, we had an electron sitting in here. This is n equals 1. And as we go farther out, those levels get closer to each other. So n equals 2, n equals 3, n equals 4, and on and on and on. So they get closer and closer the farther you get out. So that will help you answer question number 5 when we get there. One thing we haven't discussed that comes up is sometimes things say, like, let's say an electron fell from a 3p to a 2p, and you'll see this symbol written in your homework. The p's can be ignored for now. We don't need to worry about it. Essentially, it's going from a level 3 and it's falling down to a level 2. And we know when it falls to a level 2, that means it's visible light. It would be emitting visible light. So I just wanted you to kind of think through that a little bit and have a good idea that if you come into these letters, we'll address those. Unfortunately, in the next chapter is where they really address them, and I wish they didn't bring them up until then. All right, so we've got this master equation. This E is technically the energy of a photon, which, if you remember, if an electron falls, it lets out this wave, and that wave we call a photon. We'll also call it light. But one thing we never discussed in class is what causes, if that photon goes off, it can also come back in. And what causes an electron to go back up would be if it absorbed a photon. So let's say you have an atom hanging out over here. And a photon came in, and the electron was hanging here. The photon could hit that electron and do what we call excite the electron, and the electron would jump up to whatever level this, and it would jump up to the exact same level that this energy photon was. So for example, if this electron was coming from like something that was a 3 to a 1 from an atom over here, let's say, then this one would go from a 1 to a 3. It would jump all the way up to a 1 to a 3. So whatever energy level this atom gives off is what this one over here absorbs. So we call this side emission, and we call this side absorption. Cool. All right, so we've got our equation, we've got some vocab terms. Let's go ahead and see if we can conquer this homework, shall we? So the first question said, very hard to see here, but it says you've got 632.8 nanometers. And it wants you to give it the frequency. And it says use 3 sig figs. That's just because the speed of light actually only has 3. So let's go through and do it real quick. First thing, when we see nanometers, we know that nano is times 10 to the negative 9. You need to know that for the exam or you will be in a lot of trouble. So our wavelength equals 632.8 times 10 to the negative 9 meters. No, this is not in scientific notation, but it doesn't really need to be yet. All we're gonna do is use this in a problem. Okay, we're trying to find frequency. If you remember, the relationship between those two is C equals lambda nu. You could also just as easily, if you only remembered the one equation, which is h nu equals hc over lambda, and I'll just do the whole thing because I didn't write it so clearly last time. Negative 2.18 times 10 to the negative 18 joules, and then times 1 over n, final squared minus 1 over n, initial squared. So you could also use this equation and just take this portion and this portion, and you would find that the h's end up canceling each other. So you just set this whole thing equal to itself, h's cancel, and you have nu equals c over lambda. And you have your equation there as well. So either way, you can figure it out. Let's go to the simple basic one, just because we're used to it. Again, we're solving for nu. So if we have c equals lambda nu, and we want to get nu alone, you divide both sides by lambda, and that gives you nu alone. In other words, our nu equals c over lambda, which would be 3.00 times 10 to the 8 meters per second, all over 632.8 times 10 to the negative 9 meters. That cancels out meters, and our units would be inverse seconds, which is good. That's what we want. So one thing I want to make sure you guys are doing when you calculate these is remembering PEMDAS. These are both on the denominator. So if they're both on the denominator, you can either use parentheses or put a division sign in front of that times 10 to the 9, which I would 10 to the negative 9, which is what I like to do. Anytime you see something on the bottom, just throw a division sign in front of it. So on my calculator, I'm going to say 3 times 10 to the 8, just hit enter, divided by 632.8, and then divided by 10 to the negative 9. And that will give you your answer. I get 4.74 times 10 to the 14 inverse seconds. I could also write, or seconds, 1 over seconds, or I could write hertz, doesn't matter. All of those units are the same if you remember. So this would be the correct answer. Again, make sure on the bottom, you're remembering to put a division sign. If you use parentheses, that's okay too. You can use multiplication if you put parentheses around them. All right. Next, a heat lamp produces 27 watts of power at a wavelength of 6 micrometers. I'm just going to say, okay, 6.0 times 10 to the negative 6 meters, because we know it's got to be in meters. And we know micro is 10 to the negative 6. I'm like, what the heck is watts? I got no idea. Oh, good. Thankfully, they told us. It's a joule per second. So if we have 27.0 watts, that's the same as saying 27.0 joules per second. And it wants to know how many photons are emitted in a second, okay? So it's easy to figure out how many total joules. That's a big number. That's a lot of power, 27 joules. So to do that, we're just like, okay, in 1 second, we know that in a second there are 27.0 joules. In other words, 27.0 joules occur in a second. But that's not the question. It wants to know photons. But if we know how much power overall is emitted, we can figure out how many photons there are. Let me take a step back and remind you guys how this works. When an electron falls, it falls down, it emits a photon, right? Those photons have a tiny amount of energy. It's like something times 10 to the negative 20 or so, and we'll figure it out here actually. It's a really tiny amount of, and that's in joules, tiny amount of energy. So we know that this is a big amount of energy, 27 joules. And it's like, how many of these little ones fit inside here? So we've got little photon, little photon, little photon, little photon, all these little photons, and they all have just a tiny amount of energy. You want to know how many of these were needed in order to add up to 27.0 joules. That's the question. All right, so let's figure out if we can find how much one of these little things how much energy one of these little things has. And to do that, we have frequency, and that's pretty awesome because we know that E equals H nu, which equals hc over lambda. I said it has frequency, it has wavelength. I'm out of it. Wavelength is right there. Okay, so we don't need this part of the equation. You can just scribble out any part that you don't want. So E equals hc over lambda. Those are the equations. That's the equation that we're going to start with. If the energy of a single photon equals hc over lambda, we know h is 6.626 times 10 to the negative 34 joules times seconds. You're supposed to memorize it. We know c equals 3.00 times 10 to the 8 meters per second. And we're going to divide it by the wavelength, which they gave us, of 6.0 times 10 to the negative 6 meters. So to throw that in my calculator, I say 6.626 times 10 to the negative 34 times 3 times 10 to the 8. I get my answer there. And then I'm going to divide it by 6.0 if you want, and then divide it by 10 to the negative 6. And this gives me an answer of 3.313 times 10 to the negative 20 joules. If you don't know it's joules, you can go back and you always look. Meters cancel, seconds cancel. The only thing that didn't cancel was joules. So that's how much energy a little tiny one has. So how many little tiny ones did it take to add up to 27 joules in total? So I'm going to take a side note here. See if you agree with me. If this is a sack of potatoes, this is how I usually teach it in class. I have a sack of potatoes. It weighs 20 pounds. I have one potato. It weighs 0.5 pounds. How many potatoes are in this sack? And the answer is 40. And some of you might get it right away because you know that you take the big number, 20 pounds, divide it by the mass of just one of those little things, 5 pounds, and you get an answer of 40. There are 40 potatoes in that sack. Oh, you took the big, or the whole, divided by the individual, and that gave you the number of things. Okay, we're gonna do the exact same thing over here. Our big number was 27 joules. Our individual number was 3.313, times 10 to the negative 20 joules. If we take the big number divided by the little one, we'll figure out how many total photons there are. So I'm going to take 27, and just to remind you, I'm going to do 3.313. I'm going to divide by 3.313, divide it by 10 to the negative 20. And that will give me my answer. It's a big number, which we expected, 8.15 times 10 to the positive 20 photons. So I hope that made some sense. All right, on to number 3. UV radiation, I see this, I think N equals 1 right away. And radiation, I don't know if I need that for the problem at all. I haven't read it yet, but good to remember that. UV radiation and radiation of shorter wavelengths can damage biomolecules because they carry enough energy to break a bond within the molecules. A carbon-carbon bond requires 348 kilojoules. That's a lot of energy in a mole to break. What's the longest wavelength of radiation with enough energy to break a carbon-carbon bonds? Okay. So, do you remember what a mole is? hopefully you do, is 6.022 times 10 to the 23rd thing. So what this is saying is that 348 kilojoules, which is times 10 to the 3rd joules, is required to break 6.022 times 10 to the 23rd bonds. That's a mole. So that many joules per that many bonds will tell you how many joules is needed for just one. 348 times 10 to the 3rd divided by 6.022 divided by 10 to the 23rd. And here I get 6.31 times 10 to the negative 20 joules. That's great because, again, we're never going to have a number for an individual photon that's going to be higher than 2.18 times 10 to the negative 18. So this is negative 20, we're good. Negative 20, negative 19, all those we should be comfortable with. So this is how many joules, and instead of bonds, we'll just say photons. So this is how many joules a single photon has. Now it asks us to find the longest wavelength. So we have to relate this energy to wavelength. Our equation again is E equals hc over lambda equals h nu. I'm not always doing it in the same order. Equals negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared. Okay, this is wavelength, that's energy. So these parts are the only parts of the equation I need. I don't need the rest. All right, so we know that we're solving for wavelength. We have E, we have H, we have C. So let's go ahead and rewrite this, but have it solve for wavelength. Now, if I was trying to get wavelength alone, hopefully you agree I'd multiply both sides by the wavelength, right? In other words, I'll rewrite it a little better. If I rewrote it and multiplied both sides times wavelength, I'd have wavelength E equals hc. And then I want to get lambda alone, so I'm dividing each side by E. So my equation is lambda equals hc over E. Or you can remember anytime you have this situation, you can just switch this and this for each other, and it'll work. Okay, so going back to this, H is 6.626 times 10 to the negative 34 joules times seconds. C is 3.00 times 10 to the 8 meters per second. And we're putting that all over the amount of energy we found, which is 6.31 times 10 to the negative 20 joules. All right, let's solve for it, shall we? Keep it up here so you can see it. 6.626 times 10 to the negative 34 times 3 times 10 to the 8, all divided by 6.31 divided by 10 to the negative 20. Woo! And it's gonna make me count the zeros. I've got 1, 2, 3, 4, 5 zeros and a 3, 1, 5. Meters. So I'm not sure if the question, I didn't copy it all the way, but it probably asks for the answer in nanometers, I'm guessing. So this is in meters. Another way to put that would be to move this 1, 2, 3, 4, 5, 6 times. So it would be 3.15 times 10 to the negative 6 meters. Actually, now I'm thinking they probably put it in micrometers because this would be an easy switch. Remember, times 10 to the negative 6 equals micro, or 3.15 micrometers. So depending on what the question asks for, all of these three answers are reasonable. All right, last but not least, it says, determine whether each one is absorption or emission. So if you remember, we said when a photon leaves, when an electron drops and a photon leaves, that's called emission because it emits light. When an atom gains a photon, or a photon hits an atom and makes the electron go up, that's absorption. So all you're asking is, did it go up or down? Here, For emission, it goes down. For absorption, it goes up. It's that straightforward. Remember, in case they do happen to have any P's or S's or D's in these levels, you ignore them. You just look at the numbers. Here we went from a 2 to a 4, so it went up. Up is absorption. So this one is absorption. Here we went from a 3 to a 1. I don't know about you, but I agree. If you fall from a 3 to a 1, that went down. This was emission. And then here we have going from, let me write it better, emission. Here we have a 4 to a 3 falling down, and something falls down. Again, it's emission. All right. Now there was one more question on here, number 5. It was kind of moving things around, but it's based on this concept of knowing that, one, that when things go down, they emit light. The other thing I think it was wanting to make sure that you understood is that as your rings, remember the stair stepper is just another way of depicting this. If this is n equals 1, your n equals 2 is at a higher level, then 3, then 4, then 5. So as they go up, they get closer together. So if something falls in here at the top, it's got a lower energy level. It's going to emit something that's lower in energy. Whereas opposed to if it makes a big fall all the way down to n equals 1, like UV light, then it's going to have an emission of higher energy. All right, I think that about covers it. Let me know if you guys have any questions.